I'm Nisha G. Krishnan, Assistant Professor, Department of DC, Yogic College of Engineering and Technology, Kanyakumari. We're discussing about electronic devices and circuit. Let's start with
Completion of this course, students will able to explain the working of p-n junction diode and characteristic of p-n junction diode. The p-n junction forms a popular semiconductor device called p-n junction diode. In a p-n junction, on p side there are large number of holes, while on n side there are large number of electrons. Hence, there is a non-uniform distribution of charge carriers, then the charge carrier starts moving from high concentration area towards the low concentration area. This is called diffusion. P region has a high concentration of holes and N region contain a large number of electrons. Since the concentration of electrons in an N region is more compared to P region, free electrons from the N region diffuse across the junction and fill the holes on the P region. Next is depletion region. The movement of charge carriers across the junction leaves a layer on each side that is depleted of charge carriers. This is depletion region. On the N region, the depletion region consists of donor impurity atoms that having lost the free electrons associated with them and become positively charged. The depletion region on the P side is made up of accepted impurity atoms. And this is barrier potential. Since there are many positive charges and many negative charges on opposite side of the P and N junction, an electric field is formed. The electric field produced is a barrier to the free flow of electrons in the N region, and energy must spend to move an electron through the electric field. The energy which is required to move electrons through the electric field is known as barrier potential. If an external DC voltage is connected in such a way that the P region terminal is connected to the positive to the DC voltage and the N region is connected to negative to the DC voltage, the biasing condition is called forward biasing. The PN junction is said to be forward bias. When the PN junction is forward biased, as long as the applied voltage is less than the barrier potential, there cannot be any conduction. When the applied voltage becomes more than the barrier potential, the negative terminal of battery pushes the free electrons against barrier potential from N to P region. Similarly, positive terminal pushes the holes from P to N region. Thus, holes gets repelled by positive terminal and cross the junction against barrier potential. Thus, the applied voltage overcomes the barrier potential. This reduces the width of depletion region. And next is reverse biasing. If an external DC voltage is connected in such a way that the P region terminal of a PN junction is connected to the negative of the battery and N region terminal of a PN junction is connected to the positive terminal of the battery, the biasing condition is called reverse biasing of a PN junction. Operation of reverse bias diode. When the PN junction is reverse biased, the negative terminal attracts the holes in the P region away from the junction. The positive terminal attracts the free electron in the N region away from the junction. No charge carriers is able to cross the junction. As electrons and holes both move away from the junction, the depletion region widens. This creates more positive ions and hence more positive charge in the N region and more negative ions and hence more negative charge in the N region. This is because the applied voltage helps the barrier potential. Next is VI characteristics. The complete VI characteristics of a diode is a combination of its forward as well as reverse characteristics. In forward characteristics, it is seen that the initially forward current is small as long as the bias voltage is less than the barrier potential. At a certain voltage close to barrier potential, current increases rapidly. The voltage at which diode current starts increasing rapidly is called as cut-in voltage. As reverse voltage is increased, reverse current increases initially, but after a certain voltage, the current remains constant equal to reverse saturation current I naught through the reverse voltage is increased. The point A where breakdown occurs and reverse current increase rapidly is called knee of the reverse characteristics. Next is diode current equation. The mathematical representation of VI characteristic of diode is called VI characteristic equation or diode current equation. It gives the mathematical relationship between applied voltage V and diode current I. It's given by I is equal to I naught into e raised to V by eta Vt minus 1. And where I naught is the reverse saturation current in amperes, V is the applied voltage, eta is equal to 1 for germanium diode and 2 for silicon diode. Vt is the voltage equivalent of temperature in volts, and the factor eta is called emission coefficient or ideality factor. Next is diffusion capacitance. During forward bias condition, another capacitance comes into existence called diffusion capacitance or storage capacitance, and it is denoted as CD. In forward bias condition, the width of the depletion region decreases and holes from P side get diffused in N side, while electrons from N side move into the P side. As the applied voltage increases, concentration of injected charged particle increases. This rate of change of the injected charge with applied voltage is defined as capacitance or diffusion capacitance. And the formula for diffusion capacitance is Cd is equal to dQy by dV, where Cd is the diffusion capacitance and dQ is the change in number of magnetic carriers stored outside the depletion region, and dV is the change in voltage applied across diode. And the flow of charge results a diode current I is equal to Q by tau, where tau is the average mean lifetime of a carrier. And then differentiate the rate of change in number of magnetic carriers stored outside the depletion region with the change in voltage applied across diode, and substitute that value I value Q value in the current equation. We get final CD result of tau I by eta Vt. Next is transition capacitance. When a diode is reverse biased, reverse current flows to the magnetic carriers. Majority charged particle, that is electron, in N region and hole in the P region move away from the junction. This increases the width of the depletion region. The width of the depletion region increases as reverse bias voltage increases. As the charged particle move away from the junction, there exists a change in charge with respect to the applied reverse voltage. So, change in charge, that is dQ, with respect to the change in voltage dV, is nothing but a capacity effect. Such a capacitance which comes into the picture under reverse bias condition is called transition capacitance or phase charge capacitance. If the W is the width of the depletion region, when the transition capacitance is given by Ct is equal to epsilon A by W. That is, A is the area of cross section of the junction and epsilon is the permittivity of the semiconductor. As the reverse bias applied to the diode increases, the width of the depletion region increases. Thus, the transition capacitance Ct decreases.